Welcome to all. Today I will cover radius of gyration first. Then little later, after this is fully over, it will take some time. I will also give information regarding two more terms. One of them is, okay, any color will do, no problem. One of them is product of inertia, and other one is polar moment of inertia. This already you know it. This I will take up it later, not right now. First I will consider radius of gyration. Okay. Now, first remember, before I start radius of gyration, remember it's a very, very powerful term when we consider buckling of columns. In this class, after explaining radius of gyration, actually of course it is about an axis. I will write it later. Once I explain and make it clear concept, then I will give simple example connected with buckling of columns. Not too much, because later when in the strength of materials, when you consider columns, a very detailed discussion will be there. And also in RCC and steel or any structural design subject, there will be deep discussion about radius of gyration, its importance. Here, I will not give too much of explanation regarding variation, or not variation, regarding, variation of radius of gyration for different cross sections all. Okay, now, starting, consider a lamina of area A. See here, randomly placed here, area A. Consider elemental area dA, green color, let y be perpendicular distance from dA to an axis AB. Make a note here, AB is any axis, but today's discussion is AB. See, you can make a note here. When we consider radius of gyration, like moment of inertia in the bracket, this also is always about an axis. Some axis, any axis. Right now it need not be centroidal axis, but structurally centroidal axis is the most important. That all will worry later. So that axis ABC, like you can write, when I started moment of inertia, I told axis AB, some axis CD here, some axis EF here, like that. That way I will discuss here. Later, we will find about required axis AB. Then, moment of inertia of the entire area about AB equal to, see, first of all, you can make a note. Moment of inertia of the elemental area dA about AB equal to dA into y square. You can write if you want here. See, if you want, you can write. Moment of inertia of the elemental area dA about AB is dA into y square. Area into square of the distance. Therefore, moment of inertia of the entire area about AB is either sigma or integration. Now I will use integration to make more clear. You can write here integration or sigma of dA into y square. Now, integration limit, see, y is this way. See, this area, imagine, as you start from AB, this area starts at a level 1, 1 here. Area ends at a level 2, 2. Therefore, see, this y is the lower limit. And see, this y is upper limit. That is, you can suppose you call this as this y as y1, this y as y2. The limit is, you can tell, integration y equal to y1 to y equal to y2. Make a note. These all we already know in moment of inertia. So therefore, I given as an introduction. Okay, now further. This I'll remove now. Now what you do is, see, I told integration from here to here. Now some important concept, that is regarding radius of gyration. This frequently there is a color change that gives trouble to me. Okay, now see, our discussion is only for AB axis now. Remember, now consider that entire area, entire area A to be concentrated, or you can use the word squeezed. Okay, squeezed. Is concentrated or squeezed at a constant distance, some name required, say R. I will tell you what, say R. R, as shown. See, once again I show area here. See, I have to maintain the level is not required. Okay, see, same project here. This is the axis C, project here. This is the axis AB. Okay, now see here. Your 1, 1 and 2, 2 are here. This one you squeeze. This is fully squeeze. But remember, sometimes people tell squeeze to a point, but actually better not squeeze to a point, squeezed along a line parallel to AB. See, like this. Somewhere, see, this entire area, imagine squeezed like this. See, somewhere here. It is somewhere in between 1 and 2. Somewhere in between 1 and 2. See, squeezed. Very, very small area. See, sorry, not small area, very, very small thickness, this way. Any width will do. Distance I will call R. See, this R, I will use red color now. R, up to where? Up to where not required. Why? R. Area is D, area is A. Area equal to A. Squeezed. Then R. Now condition is as shown. As shown. Now right here, some condition is there. I will remove this one now. There is some condition. How to squeeze it? Not randomly squeezed. Okay, this I will remove now. See. As shown, I will continue the statement here. So that, see, at a constant distance R. Now red R I am making, so that moment of inertia of the entire area about AB, that is your IAB, is equal to that area multiplied by that R square. See, this is actually basic definition. Area into distance square. But actually there are infinite number of parts are there. This all you squeeze, and then see here, this will have different Y, this will have different Y. But here what will happen? When you squeeze here, everywhere same Y will come. So then A into R square. That is no integration along what is, see, suppose this thickness I will take T. T is very, 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 very small. Infinitely small. Very, very small. So that you cannot make out. See, so that there is no integration along that thickness. I will tell you why it's important little later. Then I can explain this R in a more technical way. That I will explain in RCC or steel or in strength of materials. But engineering mechanics, you should know what is the basic approach. Somebody may comment, I can give a better explanation. I can also give better, but I want everybody to understand. So then, then that R is called radius of gyration. Why that word gyration came, I have no idea. I am not bothered. I would have gone for Google and searched what is the meaning of word gyration. No, it is a universal word. Then radius also, doubt will come. Why you call radius? English word. Radius of gyration of the entire area A, but very important, about AB. Or you can write one more statement, I'll give it later. Or you squeeze it at a constant distance R, so that this thickness, this is very, very small. So wherever you consider in the area, distance is constant. In that case, there is no integration, simply A into R square. Why? Basic moment of inertia is, see, if you take elemental area here, area into R square, one more area into R square, one more area here into R square. Everywhere R square common, this area plus this area plus this area plus this area plus this area is entire area. That much is sufficient for you. Now, in the definition I will tell you, so it's a radius of gyration is somewhat an imaginary distance at which the entire area is considered to be concentrated at a constant distance, that radius of gyration at constant distance R, so that product of area and square of that radius of gyration will give same moment of inertia as the moment of inertia of the original. I don't know why I removed it. Area equal to A is there. I don't know why I removed it. Area equal to A. Okay. Will give same moment of inertia as the original area, moment of inertia of the original area with the fully dispersed here, see, about AB axis. Or there is no change in moment of inertia. That is basic idea of radius of gyration. It is imagination. I will give some example for you. It will be much, much more clear then. Don't be in such a hurry to understand. Don't be in such a hurry to close this one. Okay, now I will go to second part to explain more. See, I just explained what is radius of gyration. Still I have not given expression for you and definition. Wait for some time. And one more thing, anybody who is not interested in all these full basic concept all, wait for some time. I will finally give summary here. That summary is very simple. You study that one, that's all. But I am giving everything so that my course is engineering mechanics, strength of materials, structural analysis, and also later RCC and steel. That is, therefore, full structural design concepts are covered here. So that's why I am explaining. See, right here, before you go further explanation or definition or final expression, example to understand radius of gyration about an axis. Okay, consider a rectangular area 60 by 20 as shown. Okay, 60 by 20. See, 60 by 20. Consider horizontal center of the axis XX. Also another two axes, say A1, B1, another two axes. One of them is A1, B1, other is A2, B2. At 100, I first took 400, then I decided to make it 500. Some reason is there. I want to have a high distance. Okay, 500, not to scale. See, if it is 100, farad will come somewhere here. Okay, not to scale, 500, all in millimeter. Now, first let us find moment of inertia of that rectangular area about XX, then about A1, B1 and A2, B2 using parallax theorem, or you can do integration also. I will tell first integration. If those who are interested, if you want by integration, it is elemental area into y square for about the center of the axis, integration is from minus 10 to plus 20. If for second one, for this one, if you want about this axis, integration is from 100 to 120. For A2, B2, integration is from 500 to 520. This all I told earlier. But now do one thing. Instead of integration, go for parallax theorem. And parallax theorem already explained. Now you understand, that's all. Don't worry too much. By chance, if you have difficulty for parallax theorem, wait for some time. This will be very thoroughly explained. Okay, start. I about x-axis axis. See, centroid is here. This is centroid G. Centroid G here. See, here also centroid G. Centroid G here. Centroid G. I about any axis equal to Ig plus AH square. See, Ig here. 60 into 20 cube by 12. That's all. Area into 0 square. Why? Because your x-axis is also centroid of the axis. Answer is 0.04 10 to the power 6. Is it correct? What is the calculator? 60 into 20 cube divided by 12 divided by 10 to the power 6. Yes, 0.04, correct. 10 to the power 6. Now, I about A1, B1. See, we shift it by 100 millimeter. 60 into 20 cube by 12 plus area into this distance square from centroid to required axis 100 plus half of 20 is 110. This is your H. See, this is your H. This is your H. Here, your H equal to 0. It will come 14.56 10 to the power 6 millimeter power 4. You can see very huge jump. Okay, now I about A2, B2. 60 into 20 cube by 12 plus area into 500 plus half of 20, 510H whole square, 312.16 10 to the power 6 millimeter power 4. Now what we will do is, see, I will remove this one now. See, I will remove this one and this also I will remove. And I will project left side now. See, I will do one thing now to understand the concept very clearly. There is no space there. See, this, I will project this first centroid of the axis. That centroid of the axis, I will shift here, see. Light line, the centroid of the axis I will project. And I will show here little further. See, exact projection is not required. Okay. Now, you should write some statement here. Statement here. Use this area, you squeeze. See how squeeze? Width you increase, thickness squeeze. See, this way, make it flat. You spread it, see, first with respect to x-axis axis. Entire area you squeeze and place here, see, this way. Very, very small thickness. Width I am not interested, very, very small. Then let the distance from here be r. That is called radius of gyration. See, radius of gyration is the distance from the axis. This is your x-axis axis. See, this is your x-axis axis. Distance from the axis, at constant distance from the axis where the entire area is squeezed. Remember, the area equal to how much? Area equal to area A equal to 60 into 20 is 1200 mm square. Now, as per definition right here, I about x-axis equal to A into r square. A into r square. And it should give same moment of inertia as you got. Therefore, you get 0.04 10 to the power 6 equal to area is 1200 into r square. R about which one? R about xx. R about xx square. You will get r about xx equal to, I don't have to calculate, I know it. It is that thickness by root 12. Okay, I'll calculate. Equal to 0.04, see, 0.04 10 to the power 6 divided by 1200, or it is root of I by A. I will tell you later. See, it is formula is square, see, I equal to a r square, r equal to I by a, it is a root of I divided by a. I about xx by a later, not now. That area by 1200 equal to root answer equal to 5.7735 millimeter. Actually, I know the answer. It is the thickness by root 12. See, 20 divided by root 12. It is same. Answer 5.77. I know about it. Okay. Now, that means, you write here, that means, okay, see, this distance is very small. How much you got? 5 point something. Or you write one thing, write one more sketch here. So it is shifting by, see, this is 20 mm, this is 10 mm. So if the rectangle is here, see, if the rectangle is here, to get radius of gyration, you squeeze it somewhere here. See, squeeze it somewhere here. Somewhere here. At what distance? At 5.7735 millimeter. Now see, this is the radius of gyration, r about xx. So some answer came. Now further, actually I can tell further. No, that's all not required for you. Now do one thing. Consider the second one. Now consider, to understand correctly, A1B1. Consider that A1B1. Now concept will come. See, the concept will come now. Actually, a very concept is there. Consider, statement not required, consider A1B1. Okay, see, I will again project here. See, I will project the rectangle. See, this is the original. See, you should write statement here. This is the original rectangle. Your A1B1 is here. See, A1B1 is here. A1B1. Now, what you do is, you squeeze it. Somewhere, we don't know where, squeeze it. Remove this one. Any width will increase now, see, width will increase. Very small thickness, okay. So that this is your R with respect to A1B1. So that, once again, this area equal to how much? 1200 only. It will not change. Area will not change. So that, see, you squeeze it here. You write here, squeeze, you should write statement, squeeze the area and place it R A1B1, so that I about A1B1, whatever you got, I about A1B1 equal to area into R about A1B1, R about A1B1 square. I A1B1 is how much? 14.56 10 to the power 6. Area is 1200. Therefore, your R about A1B1 will come 14.56 10 to the power 6 divided by 1200, root answer equal to 110.15 millimeter. 110.15 millimeter. 110.15. Next number, actually not third decimal sufficient. Answer equal to 1514. Okay, 110.1514 millimeter. That means, see here, this is 110. Here, that squeezed area shifted by how much? Answer. First time it shifted by how much I told? 20 divided by root 12. 5.77. Nearly whatever remaining thickness is there, half the distance it moved. But this time it is squeezing. Distance is moving by very small, only 0.1514 millimeter. That means this is, you can tell, almost equal to that 110 millimeter used as H. But a little more. Or, now you write statement here. See, therefore, you project that one, the second area. See, the second area, this is the area, area here, little bigger. Okay, I'll project here. Understanding is important. Area is here. And I'll remove this one now. With respect to your A1, B1, A1, B1, this should be, see, this is the centroid here. Earlier, centroid was here. You have to squeeze it slightly above, very, very micro, slightly above. See, squeeze it slightly above. Okay. See. Now this R about A1, B1 equal to 110.1514 millimeter. That means as the distance of the required axis moves more and more away, see, dispersion is more. When dispersion is more, moment of inertia predominantly depends on distances only. That Ig becomes negligible, or the shifted, you can write here, this is only 0.1514 mm more than what? More than that H of 110 millimeter. So this squeezed area is slightly above. Okay, now see the last one. Same way, see, consider the last case, A2, B2. Now see what happens. Beautiful answer you will get. A2, B2. Again I project here, see. Your axis is somewhere here. Far, far away, see. A2, B2. A2, B2. First what you do? First you squeeze it. Somewhere squeeze. See what I wrote here? Okay, then remove the removing area. So that this area is still what? Actually it will be bigger, it will become, see, it will become this way. No, that's not important. Because our integration is this way. Area is still equal to 1200 area. So this is your R A2, B2. Now I about A2, B2, for the original should be equal to area into R about A2, B2 square. A2, B2 is 312.16 10 to the power 6. Area is 1200. So your R about A2, B2 equal to, now see what happens. See that H is 510. It will be slightly more than 510. Almost 510. See, 312.16 10 to the power 6 divided by 1200 equal to square root, answer equal to 510.03. Further small. R will come 510.03 millimeter. Or, right here, or if that, see, for that rectangle of this way of 60 by 20, its centroid is here, see, its centroid is here. If you take the axis A2, B2 very far off from here, then, see, I'll do one thing now. I just put dotted line here so that it will be clear for you, see. It's the original area. 20 is somewhere here, 20 here. This can be squeezed into, see, this way. This way, this entire area can be squeezed as a line area, or at a R of R A2, B2 equal to 510.03 millimeter, whereas from A2, B2 to centroid is 510. So this shift is only 0.03 millimeter. Now, just to understand, you try. Suppose the distance is not 500. See, suppose the distance is not 500. You take very high value. Say, very high value, 4000. See what happens now. Then your I about, suppose some I about this axis for by original calculation will be equal to, you can calculate yourself only how much it is. 60 into 20, you can try yourself. 60 into 20 cube divided by 12 plus 60 into 20 into 4000 plus another 10 whole square. It will come divided by 1 10 to the power 6. 19296 19296.16 10 to the power 6. This will be equal to your area of how much? Area of 1200 into r square. R square. The r will come divided by 1200 into 110 to the power 6 equal to root answer. Answer equal to 1010.004. Whereas from here, how much I told? Not 10. No, something wrong. Something wrong. 1 minute. 60 into 20 cube divided by 12 plus 60 into 20 into 4000 plus 10 close square equal to root answer 1213. It's not visible line. This is a problem here. Display 138910. Oh, sorry, it's wrong. 138910.6187 10 to the power 6. Then your r will come. This answer, see, equal to what? This I will be equal to what? This I will be equal to A into r square. R square. Then area is 1200. 1200. Your r will come into 1 10 to the power 6 divided by 1200 equal to root answer equal to 10979. Something wrong in the calculation. I don't know what is the problem in the calculator. 10759. It is something nonsense. One minute. But no problem. Sometimes it happens. 60 into 20 cube divided by 12 plus 60 into 20 into bracket 10 plus 4000 close square equal to divided by 10 to the power 6. Oh, it is 19296. So again, I don't know why it's happening. 19296.16 10 to the power 6. This should be equal to area into r square. Area is 1200. Your r will come into 1 10 to the power 6 divided by how much area? 1200 equal to root answer. Oh, it is correct actually. It is correct. That 4 looks, because of a calculator strain in the, there is some stain in the calculator display. Actually it is 4. I am unnecessarily wasting my time. It looked like 1. No, it is 4010.004. See, now from here to center is how much? To centroid is, see, to centroid here, G, red color. From here to centroid is, sometimes it happens what to do. Centroid is 4000 plus 10 is 4010. See, 4010, 4010.004 means what? That is, you can tell entire area is almost squeezed at centroid. That is why in so many times in structural engineering, if the area is dispersed at a very high distance, I will tell you how high you should decide at that time. That is logic. Or at that time, your judgment. Then instead of using Ig plus AH square, people will directly calculate I equal to directly AH square. They will ignore the term Ig. They will tell Ig is so small. It is like 15, 20 rupees plus 35 crores or 40 crores. 45 crores plus 15, 20 rupees. Who will bother about 15, 20 rupees? So that's why what? You can now decide as the axis is shifting away and away and away and away from centroid, radius of gyration approaches to the distance of the centroid from the axis. See, radius of gyration approaches to distance of centroid from the axis. That is, I will tell you one more thing. See, suppose there is an area here. See, an area here. Area here. Okay. Some area here. Suppose at a huge distance here. See, this distance is centroidal distance is something, say, anything, h. If you squeeze here, it will become this way. Then this is your R. Your R, red color, R about this axis, R, will be almost equal to h. That is, there is no integration along this one. This is only to understand. Okay, now I will go further, little more, so that for those who want concept, I will give information. Others all need not worry anything about it. You need not bother. See, make a note here. Little later, I am returning back to class. Some will tell, so you are not in the class now. I am in the class. I am in the class for those who are interested in concept. Then I will tell I equal to AR square and R equal to root of I by A. And then I will tell what is the significance of R now only, so that I don't have to once again come back here. Remember, what I am going to explain now will be very, very, very thoroughly explained later in strength of material when I go to column, and furthermore thoroughly in steel structures and RCC when I go to columns. Right now, see, consider a column. Consider a column. See, this way. Any end conditions, we don't know. It can be fixed at the ends. Okay, now, for a column, based on its end conditions and length, there is a term called effective length. Right now, you believe me. Effective length. That symbol, I will take L effective. And then, there is a term called, you know it, radius of gyration. Radius of gyration. I am discussing the case when effective length is constant with respect to any axis in cross section. Don't worry about it. Then, radiation that is called R. Then a term will come called slenderness ratio. Slenderness ratio. Symbol is lambda. Lambda is equal to L effective by R. Of course, at that time, if the effective length is constant with respect to any axis, it will be R minimum. That is least R. Least R. This term is a very bad number. See, this lambda is a bad number. Bad thing. Bad. Bad means as the length of column increases, slenderness ratio will increase. And as R decreases, column becomes thinner and thinner. See, then huge length, thin column. See, L increases, R decreases, length increases, and this R is directly connected with the thickness here. It is actually thickness by root 12. Okay, then see, the column will tend to buckle. See here, it will tend to buckle. So, this slenderness ratio lambda, L effective by R, it is actually will tell you how slender column is. As the lambda increases, column becomes more and more slender. As lambda decreases, see what happens now, show here, I will show you. as lambda decreases. See here, length reduces. See, first time I told you, length increases, thickness decreases. See, it is likely to buckle, very weak column. Whereas, as lambda decreases, either length decreases or the thickness increases, then it won't buckle. See, this you cannot buckle. It's very strong. That is, column will, as lambda become lesser and lesser, as your lambda becomes lesser and lesser, column will tend to become a short column. Short column. It will become a short column where failure will be by crushing. No buckling. No buckling. And as lambda increases, column will tend to become more and more slender. Therefore, ever it will tend, then buckling chance is more. Buckling chance more. And as lambda becomes very, very high, then that column is called a long column. Long column. It will fail only by buckling. I think that much is sufficient here. People who already know about this one, they understand. Others all leave it. Okay, now, after I started the class and till here, only those people study who are interested. Others, go to next part. I will go to next part. But next part is very important for subject. So, now come to a simple and now subject, back to subject. Now required for everybody. Radius of gyration of an area about an axis, any axis, is an imaginary distance at which, of course, imaginary constant distance at which the entire area can be assumed to be concentrated or squeezed. See, squeezed means constant distance. So that moment of inertia of the area about that axis can be written as product of area and square of that distance. That distance means radius of gyration. That is what? So therefore, see, I write here now. Now, see, consider area A randomly. Consider an axis AB. AB. Okay. Now, let IAB be moment of inertia of the area about AB. About AB. See, that is equal to what? This you can get by integration of dA into y square. I won't waste time now writing everything same way again, day by day, same thing. Okay, this is already there. Now, what? Consider that area to be squeezed, to be spread at constant distance R AB from AB. How? See? This way. Somewhere here. This is AB. This is your RAB. Area is A. IAB, so that I about AB equal to A into RAB square. RAB square means that is right here, moment of inertia right here. After squeezing and finding I by AR square, moment of inertia will remain same as the earlier area. Moment of inertia should not change. To give the same moment of inertia, you can add one extra in the previous definition also, to get the same moment of inertia as we get by basic calculation. Okay, now that's all. Nothing further. Little more I have to tell and stop the class. Now, remember, first of all, make a note. Like moment of inertia, for radius of gyration also, axis is considered. Okay. Now write last part. In general, I equal to AR square, or that is, you can write here, that is, if you want I about XX, it is area into R about XX square. Or if you write I about AB equal to area into R about AB square, that way. Sufficient. Therefore, you replace what you get, R about XX equal to, when you write I equal to AR square, or you can tell R equal to root of I by A. In general, therefore, if you consider here, in general, R equal to root of I by A. R square equal to I by A, R equal to root of I by A. Or if this is general, if you consider axis, then Rxx equal to square root of I about xx divided by area, Rab equal to square root of I about yy by area. Later, suppose you want R about yy, it is root of I about yy divided by area, etc. So in future, make a note here. If you are asked to find radius of gyration about any axis, what you do? First find moment of inertia about that axis, and then divide by the area, take square root, you get radius of gyration about that axis. See, now, actually, to me, radius of gyration is not so simple. Simple only, but it is no confusion. I can see that one. How do you see, sir? That is my inner mind. That I will tell you when you go to RCC or steel later, or strength of materials. Not right now. Moment of inertia I told. Okay, now, over. Now we are ready to enter the calculation. Before that, last two terms I will finish today. See, one of them is called polar moment of inertia. Actually, I already known it. Polar moment of inertia. Polar, see. Polar moment of inertia of an area is moment of inertia of that area about an axis passing through a point in its plane, in the plane, and passing through a point in the plane, and that axis is perpendicular. Actually, single line is sufficient, perpendicular to plane of the area. Simple language, plane of the area. That is, see, suppose there is an area here, randomly. You do one thing, randomly take two axes, randomly. Take O, X, randomly, X and Y. See, consider elemental area dA. See, Now you require about a point. See here, I polar is, see, now here consider OZ axis. So I polar moment of inertia, polar moment of inertia about OZ equal to sigma dA into this distance square. That is called Z into Z square, but usually people call R square. They take radial R. This is X square, this is Y square. This I already told in perpendicular axis theorem. More I will not tell. Or polar moment of inertia. See, suppose there is an area here, any area. Polar moment of inertia about an axis. See, I can't show it here. Either about this axis or about this axis or this. Not, see, this is moment of inertia about axis lying in the plane. Now, it is actually what? About an axis perpendicular to the plane of the area, which can pass through any point. Usually you require centroid. So I see, even if I show this way, it's actually this way. See, perpendicular to the plane, I is polar moment of inertia. Okay, sufficient. Furthermore, I already told you earlier. That is why when you go to, I'll tell you now, see, when you go to strength of materials, see, when you go to strength of materials and torsion chapter, there, this is the cross section of shaft. Shaft is like this. See, this is the what? This axis is perpendicular plane OZ. You take elemental area dA here at anywhere, elemental area dA here at radial distance R. There you will get a term sigma of dA into R square. That term in the see, area into see this OZ is perpendicular to the plane. Then that term will be replaced by I about OZ, or it is called IZ, or it is called IP there. That is polar moment of inertia. In the torsion chapter, I will explain. Now I told only what will happen later. Okay, now this all. Therefore, this in the summary I will tell you. In any examination, if they ask polar moment of inertia, what you do? You find moment of inertia about two mutually perpendicular planes lying in the plane, and then add those two, perpendicular axis theorem. I will explain later. And then lastly, one term we will only consider here and brief explanation, because it is out of scope of our subject here. Product of inertia. This is required for product of inertia. Unsymmetrical bending. Inertia. See, again, consider an area A. Area. Consider two axes, OX and OY. You write statement on OX, OY. Consider any elemental area. Let this distance be Y. Let this distance be X. Now, I will dictate something. You write. dA into Y is first moment of the area, elemental area about OX. Sigma or integration will give moment of the entire area about OX. Same way. You should write it. dA into X will give first moment of the area about OY, and sigma or integration of dA into Y will give first moment of the area about what? OY. Then dA into Y square will give moment of inertia of the elemental area dA about OX. So moment of inertia of the entire area is sigma dA into Y square. You know it. Then write. dA into X square will give moment of inertia of the elemental area about OY axis. Sigma of that one or integration will give you moment of inertia of the entire area about OX. But in some structural engineering class, in some structural engineering subject or in some chapters, we will come across a term dA into x into y, area into x distance into y distance. See, only dAx is moment about what? Y axis. Say sigma means what? Total moment. Or see, if both are x, it will be moment of inertia. See, if dA into x is moment of inertia, dA into x square, dA into y is moment of inertia about OY axis. But dA into x into y you will get. This term is called product of inertia. Product, see, x, y both are there. Product of inertia of elemental area with respect to OX and OY. OX and OY. That's why it is called IXY. See, IXX means moment of inertia about XX axis. IYY means moment of inertia about YY axis. IXY means product of inertia. Therefore, product of inertia IXY for entire area equal to either sigma of dA into x into y or integration of dA into x into y. That's all sufficient. Furthermore, you won't understand what is the important. It comes in unsymmetrical bending. In the strength, when I go to further subjects, when I come across unsymmetrical bending, then I will explain the meaning of this one and how to calculate that one. Under normal cases, not required. Or by chance, someone will tell, sir, we want some problem to be solved. Okay, I will solve. But at that time, I will tell you, you take the procedure from me, but the principles don't bother too much now. You won't understand now. Okay, that's all. Now remember, everything is over, basic theory over. Now we are very, very important. I will give, now only I will tell, next class onwards, be very serious. Because we are entering back to problems now. But before that, I will explain thoroughly all the concept, not that mind. So I will not tell what feeling or story. I will make it clear for you how you should understand. See, I for rectangle, triangle, semicircle, circle, quadrant, parallax theorem, how to use it, everything I will explain. One mega class will be there, then marathon questions. Okay, thank you. We'll meet next time.